electromagnetic induction. The word induction means to make something happen. So if you induce something, you're making something happen. You might have heard that. I think one of the most common ones would be if a lady's pregnancy is going too long, she hasn't gone into labour, they'll induce her. So they'll induce the birth by giving her some drugs that will make labour start to take place. So that's induction. So we're looking at the interaction between electric and magnetic fields that's going to induce or make something happen. So there's an actual definition down here. Electromagnetic induction, the production of an electromagnetic force, I'm all tongue-tied this morning, electromagnetic force or EMF or voltage. Now, they are the exact same thing. That's what they mean by or voltage. It's not alternatives. They are the same thing. It's just two different terms for the same thing, electromotive force or voltage. So it's the production of an electromotive force or voltage across an electrical conductor due to its dynamic interaction with a magnetic field. Now, the key here is the word dynamic. You have to have movement. Either the magnetic field has got to be moved, so you're moving the magnet around, or you've got to move the coil of wire around so that the flux, the magnetic field lines are changing. When there's no change, there's no EMF produced. So if you look at the diagram they've got here, the one in the center, nothing is moving. They're not moving the magnet, they're not moving the coil, and the little arrow on the meter is pointing straight up. So that would indicate that there's no current, there's no EMF or voltage being produced here. The rule with these things is that the current that's induced here will produce a magnetic field which opposes changes in this magnetic field. So if we want to oppose the action of a north coming towards us, we need to have a north here to repel it. So if you remember your solenoid rule, it's this right hand with your fingers coiled. So we want a north on this right hand end. So the thumb points north, your fingers curl up the back and down the front. And that's exactly what this diagram shows. The current here is going up the back of the coil and coming down the front. So that would produce a north at this end of the solenoid, and that would act to oppose this change here, the change of bringing that north in close. And our little indicator here, our little gauge, is flicking to the left. Whether that be an ammeter or a voltmeter, it wouldn't matter, it would flick. This one over here, they're pulling the north away. So if we wanted to oppose the north moving away, we would need a south pole here and a north pole there. So same again, it's your right hand rule. This is your north pole. Up go the fingers, around and down behind. So if you look carefully at the diagram, you'll see they've got a current there going up the front of the solenoid and down the back. So that would produce a north at this end and a south at that end. And that would oppose the motion of pulling this north away. Okay? So they've got a definition down here of EMF. It's just a difference in potential that what does it say? Tends to give rise to an electric current. It is measured in volts. It's just voltage. So what things are going to determine the size of the voltage that you get inside here? What sort of things do you think are going to make a difference? So if I'm inducing a voltage by moving this magnet in, well, it would make sense that the size of the magnet, the magnetic field strength, would be important. How fast I'm moving the magnet would make a difference. The area, cross-sectional area, we've seen that earlier. The cross-sectional area is important. The angle is important. And in this case, you want the angle to actually be 0. 90 degrees up this way, if you bring the magnet in down, you won't actually induce a current. So this time we want the magnet coming in from the end. The number of turns of wire, those things are all going to make a difference. Now they're all listed down here at the bottom of the page. You must know what those symbols mean. And I'm pretty sure that this one here is a typo. That should be a small n. So you can go ahead and make that change in your textbook. I know you hate doing it. It should be a smaller n. The number of turns is a small n. It says it's even a small n here, number of turns. Total EMF is n times EMF of 1 turn. All right, so over the page we get this tricky looking formula, but it's not as bad as it looks. Remember, this EMF is all just voltage, changing the potential difference. So that's nothing. They're not separate entities. They stand for the one thing. Don't go looking for what a capital E, a capital M, and a capital F is. EMF is just one thing. So as we said, the number of turns, that's what we expected. Now, the triangle means change in, so it's not a separate variable. Change in the magnetic field times the area at right angles divided by the change in time. So this is what gives us that rate of change. So how quickly you're changing that magnetic field. And then a substitute in here, well, if it's at a different angle, we're going to have to use cos theta. Earlier we learnt that the magnetic flux was magnetic field by area by cos theta, so they're substituting in phi instead of that part there. So you've got two formulas now. Oh, and there's a negative at the front. Number of terms, the change in the flux over the time, so the rate of flux change by the number of turns. Negative sign indicates that the induced EMF acts to oppose any change in magnetic flux, and that's what I talked about before when I was doing those things with my hand signals. All right, now down here it looks like we've got a whole heap of formulas, but it's not. It's an expansion of this one original formula. So in the first case they've gone, all right, the magnetic field strength is going to change. So they've just taken out the brackets really and changed it to the final magnetic field minus the initial times the area times cos theta. So it's just a rearrangement of the formula, but they've gone magnetic field final minus magnetic field initial for the change in the magnetic field. So you do that if you had a changing magnetic field. This one's the same, but it's a changing area. So final area minus initial area. I really don't know why they went to all that trouble. If you've got this one up here, that's all you need. That one and that one. You don't need to worry about all that. They're just common sense. So we're not going to worry about it. The things that are going to change are the field strength or the area or the angle. But they've done it all out in longhand, which is a bit strange. All right, we're up to worked examples. I might do that in a separate video.